Okay, so you guys are, let's work here together, okay? So tau equal to what? What is my marker? I guess I dropped it. Okay, so tau equal to what, right? So we know, first thing is we want to write the position versus time equation here. So if you guys remember, it is xt, for damped oscillation, it's xt equal to what? A e to the power minus t over tau cos 2 pi ft, okay? First, we want to find few things. We want to find the amplitude, right? Because we want to eliminate as many unknown as we can from this equation, right? Frequency, we already know, we have a time period, we have frequency, t is, and this is, so we don't need to worry about time t, so tau is the one we want to find. So let's look at the initial condition. Initial condition, meaning when time t equal to 0, what happens to this equation one? Let us see. At x t equal to 0, we have a e to the power minus of 0 by tau, and then cos 2 pi f times 0, right? So this quantity becomes what? 0, total becomes 0. So cos 0 is 1, we know cos 0 is equal to 1, so this part is 1. Anything, e to the power real is 0, right? That negative sign real doesn't matter there. Anything to the power 0 is also 1. So this also becomes 1 here. 1 times 1 is just 1. We are left with a here. And then x at t equal to 0. What's the value of x when the time is 0? When time is 0, the value of x is 0.6. So we have 0.6, which is equal to our now a. Okay? So let's rewrite this. Our amplitude a is 0.6 meter, right? We need the unit here, amplitude. This is one step here. We need to find what is the tau, right? So I'm going to erase this part here, okay? Because I need more space to work on. Now this is the initial condition, and we find amplitude. Now next situation is we want to look at, when time t equal to the period t, which is 4 seconds, right? We've determined that in A. So you need that information. To find the tau, you need the information about period, okay, for this case here. So when t equal to t, 4 seconds, capital T, period is 4 seconds, what happens to this equation here, equation 1? Equation 1 becomes like this, x capital, I'm going to just write t, okay, in place of t here, equal to A is just our 0.6 second right now, right? E minus, in place of t now we have a period t which is 4 seconds. So I'm going to just write 4 divided by tau, and then cos, so 2 pi times f, what is our f? Cos 2 pi, our f was 1/4, right? Frequency, times, this t is period which is 4 now, okay? You guys see? So this 4 and this 4 cancels out, so we have here cos 2 pi. So remember, cos 2 pi is again equal to cos 0, which is equal to 1, okay? So this whole quantity becomes 1 here, so we are left with something. So let's see. So x at period t, what is t? T is 4 seconds. So at 4 seconds, what is the value of x? At x equal to t, capital T, which is a period at 4 seconds, the value of x is, we want to go up here. So this is the value of x, and if we, dot, the value is 0.4, okay? 0.4 equal to then 0.6 e to the power minus 4 by tau. Alright, now this looks much simpler, right? I'm going to erase this part, guys. Here, so now it's just doing algebra here, right? So let's do this. I'm going to bring this e over here and then take this over here, okay? So then when I bring this e over here, this becomes just simply e4 by tau equal to what? 0.6 by 0.4. This is you can really write this, right? 3 times, right? So that's 3 by 2, right? And then now let us take log on both sides, natural log. So taking natural log ln, we get on both sides, okay? We get log e to the power 4 by tau equal to log 3 by 2, okay? Now, do you guys remember the property of the log, right? We have this log of y to the power a is simply a log, natural log, okay, ln y, okay? So this power here, it comes in front here. That's all happening here. So we can do the same thing here. So we can write 4 by tau log e, which is equal to log 3 by 2 on this side. Also remember the property of natural logarithm, ln e is just 1, right? So in place of this guy, we can just write 1. We are not going to write that 1 here. So we now just have 4 by tau equal to ln 3 by 2. Okay? Let me get another marker, guys. This is really fading away. Alright? So I'm going to erase this guy here. So basically, here tau, right? We can take this tau over here, bring this log down here. So we can write tau equal to what? 4 divided by ln, meaning really log 3 by 2. Okay? So put this in your calculator. Make sure you put this log, natural log, not the base 10 log. Okay? So that's important, and write down the value you get there. So it turns out this is a 9.8 second. Okay, so that's the tau. 8.9 or 9.8? Yes, 9.8 second. So this is the time constant. 9.8 second is the time constant for decay of oscillation. Alright, so this is how you find the time constant. So please take a moment to go through this, copy this. Okay, so another question for the same graph. Just see how they see. So how much energy has been lost in the first 4 seconds? Okay, so how can we determine how much energy has been lost in this first 4 seconds? Meaning starting from here all the way to this time, how much energy is lost here? So again, take a minute to look at this if you can, and see if you can do it. you able to find the amount of energy lost here in the first 4 seconds? Okay, I'm going to erase the question. I need that space. Okay. So, to answer this question, let's look at here. So let's look at it. We are asked how much energy is lost in the first 4 seconds. We don't really need to know anything in between, right? When we want to look at the energy, right? So just the initial point and the final point, that's the two things, those are the important. Initial point, it starts with some energy. It has some energy. What is the energy? It is in the form of potential energy, right? Which is at, time at really t equal to 0, it has a potential energy. When it's the object is, over here we have some potential energy, right? So that potential energy, as the object starts to oscillate, potential energy is kind of now decreasing with time, and then, but then after, like at 4 seconds, it has lost some energy. So this object cannot come back to the same initial position where it started. So it's not coming at 0.6. Rather, it lost some energy and it's coming up to only 0.4 meter high. Okay? So you see? So then, the amount of energy lost must be the total energy we had initially and the difference between the total energy we had initially and the total energy we had at 4 seconds. Okay, so that should give us the difference. So really this part should tell us how much energy is lost. Okay, so we are going to do that. So let's write it here. Initial potential energy Ui is as initial potential energy, which is half k x squared, right? Or let's write xi. Okay, I means initial. Okay. So we can find what is our Ui. Then Ui is really here half time. Well, let's write the value afterwards, okay? And then this is another equation. I'm just writing Uf is the final potential energy, which is at 4 seconds, is again half k. Spring constant doesn't change for this oscillation, right? However, this position changes, which is xf squared. Okay, final meaning at 4 seconds we have a different final position. Okay, so the change in potential energy delta U, which is given usually by Uf, right? Final minus initial gives us the change in the potential energy. And then if we write this down here, equation here, it becomes half kxf squared minus half kxi initially square, right? So next is just algebra. See, this thing and this thing we have a common here. So we just take that out, half k times xf square minus xi square. Okay? So now this is a nice equation we have here. Let me see if you can see this part here in video or not. Okay, you guys can see it. Okay. So I'm gonna erase this part here and then write it down up. So our delta U is equal to half k times, I'm just gonna repeat that step here, okay, xf square minus xi square. But then we have given the value of k. What is the value of k? We were given at the beginning and it has 200 Newton per meter, right? What is our final xf? What's our final position? Our final point here is at 4 seconds, right? So at 4 seconds it has the position at 0.4 meter. So 0.4 meter, and then we need to square that, minus our initial xi position at time t equal to 0 is what? This is at 0.6, okay? So 0.6, again you square that, and then if you put this in the calculator, you should get some answer there, and it turns out that this answer is negative 10 joule. Okay, so the answer is the change in the amount of energy lost is 10 joule. Okay, amount of energy lost was 10 joule. This negative sign really tells us energy is lost. So negative sign indicates energy is lost. Okay, so okay, alright guys, so this is about it. These are the questions for you to review for exam, and then of course you want to practice more, right? So practice the questions from the lectures that we have solved in the lecture. Practice the question from homework and you guys should be fine. I'm not gonna make really hard exam, okay, let's be honest. If you have been practicing these lecture questions we have done in the lecture and the homework, you guys will be totally fine. All right, thank you.